Hello, hi. Welcome to Introduction to Differential Equation. This is just a first lesson and we're going to learn about ordinary differential equation ODE and partial differential equation PDE. But what is differential equation? Let's start with that question. What is differential equation? So you can see we have equation, right? So it has to have an equal sign. Okay. So a differential equation is basically an equation that has derivatives. And when I say derivatives, it could be, the first order derivative, second order derivative, it could be any order or a mixing of those. A simple example, something like y double prime plus y equal to x. So that's a simple differential equation, a simple one. Here y is the unknown function. So y, think as a function of x. So we're looking for what are possible solution, what are the possible function of x that satisfy this differential equation. Just like when you solve a equation. So for example, if I say solve 2x plus 1 equal to 5, right? Solve this. And when you solve, you get x equal to 2. So this means if you replace x by 2, this equation is true. Exactly the same way, here y is the unknown function. So in the situation of algebraic equation, you're looking for unknown number. So your x represents some number. But here my y represent functions. So we're looking for, so y here is the unknown functions. So your job, so when we say solve a differential equation, that means find all possible functions y of x. When you substitute this in place of this differential equation, this equality should be true. And of course, we are going to look into how you actually solve this type of differential equation that's coming up later. In fact, many of the integral that you learn in calculus 1 and calculus 2 can be rephrased as a differential equation. So for example, think about this integral or the antiderivative of x. So you want to, so this is a calculus 1, right? And we all know the answer, right? Is half x squared plus c. Now I can rephrase this antiderivative or this integral as a differential equation question, simply writing y prime equal to x and ask you to solve this differential equation. So let's think about what we are doing here. Remember, y is the unknown function, right? So you're thinking y as some function of x. So what my function, so in this case, solving means find all function y of x whose first derivative is equal to x. So we're looking for all function y of x so that the y prime is equal to x. What are those functions? So of course, in this case, to solve, to figure out the y, you need to take the integral of x. And of course, you get the answer half x squared plus c. So it's a very simple baby differential equation, right? Which actually another way of writing an antiderivative from your calculus 1. And we already know how to solve. It's a simple integral, right? Right away, you see that the solution to this differential equation y prime equal to x in fact has an infinity many solution, right? Unlike an algebraic equation where you only have one or two solution in this case, right? In some algebraic equation, of course, you can have infinity many solution. So here you can see that for each value of c is a solution to this differential equation. So to write a few, for example, one solution is y equal to half x squared if I choose c to be 0. Another solution is y equal to half x squared plus 2, right? If I choose c to be 2, and etc, etc, right? So for each value of c, I get a solution. C could be any real number. It doesn't have to be integer or whole number. It could be fraction. It could be square root of 2, any real number. So there are several ways you can write a differential equation. So we have, so for example, if I go back to this first example, right, y double prime plus y equal to x, I can also use this notation, the D notation, right, that you learn in calculus 1, right? So this is another way of writing y double prime, right? So this is just another way of writing the same equation. In some way, this is better because you know what is the independent variable, right? Just looking at it, you know the independent variable, right? Um, in this case, of course, you can look at the right hand side, which is x. So you know the independent variable is x. But for example, if I give you something like just this, right? Just this differential equation, of course, the y is the unknown function, but y, is it a function of x? Sometimes we might want this a function of t. We're not 100% sure, and it's okay. You can choose any independent variable as you want. Many times we use y of t, and we use t as the independent variable because many times the independent variable represent real life situation, and typically it is time. So we use t many times. So t or x, we're going to stick with that. um, so in this case, and then this is a very interesting differential equation. Think about that. So we're looking for all function f of x, right? All the function f of x, so that the second derivative added to the original function is equal to 0, right? It's an interesting question to ask, right? What are all possible functions so that when you take the second derivative, add it to the original function, you get 0. So you can actually, we typically use y instead of f, the f notation, the f of x, we use y of x. So we're going to stick with that. But this is another way to rephrase that same differential equation. So this type of differential equation where we use a single variable function. So here the unknown is a single variable function. It's a single variable function. All the function that you used to learn in calculus 1, calculus 2 is all a single variable function, right? Y equal to sine x, y equal to x squared, y equal to e to the x, y equal to ln x. Those are all single variable function. But of course, in calculus 3, you learn that there are multivariable function, right? In that case, we can have a differential equation where the unknown is a multivariable function. So for example, I can ask something like this: the second partial derivative of some function, let's say phi, with respect to x twice, plus the second derivative of this function phi with respect to y twice, will give you 0, right? That's a differential equation, right? In this case, my unknown function is phi, and phi is a function of x and y. So this is now calculus 2, right? Sorry, calculus 3, where you learn about multivariable function. So we're looking for all two variable function so that the partial derivative, the second partial derivative of this function phi with respect to x twice, added to the second partial derivative of this function phi with respect to y twice, when I added them up, the answer is 0. So this type of differential equation is what we call PDE, stand for partial differential equation, because it involves partial derivative. And the all the example that I did previously, right? For example, this one is called ODE. So it's called ordinary differential equation. So in short, so let's write down um, the summary. So here the ODE will means that the ordinary differential equation. PDE will stand for partial differential equation. So in this course, where 99% of the time we're going to concentrate on the ordinary differential equation. So again, the ordinary differential equation, the unknown function is a single variable function. It's a function of x only, or a function of t only, whichever variable you choose. On the other hand, partial differential equation is the unknown function is a multivariable function. It could be a function of two variable, it could be a function of three variable. So there are many possibilities. So once you go beyond single variable and you're looking for the unknown function as a two variable function and three variable function, etc., that's become partial differential equation. So we're going to concentrate on the ordinary differential equation. So that's it for this episode. See you later, and always remember, do not fear math and believe yourself. Bye bye. Thank you.